Hello everyone and welcome back. So now I want to go through several of the other methods by which you can do linear regression in Excel. We're going to focus heavily on this final step here, regression analysis tools, which is what I really want to get to. But just to note, there are really four main ways that we want to cover in class this semester, at least in this week. Calculate using a spreadsheet formulas below. I have in this PowerPoint slide that's posted online or will be by the time these videos are uploaded. We can use these expressions for a two coefficient model, linear model, just mx plus b model. Here we define the coefficients as b0 and b1, but I go through the derivations in the slides on how you can derive these expressions to directly and analytically calculate the your best coefficients for this model. We've also already covered how to do trend lines to do this, and there's also built-in functions within Excel to find slopes. Actually, you can find the slope, intercept, and the R-squared value through simple functions in Excel. And I'll just again show that here just for sake of completeness. This is using the same data set in my R-squared video, but we can say intercept, and you enter in all the known y's, and you enter in all the known x's as described in the requirements. Hit enter and you get the intercept, and you can do slope, comma, and here we can go comma, and you get the intercept or the slope, and then we can also get the R-squared value of the system, comma, and it's 0.827 as we calculated. So we have that approach as well. It's just entirely up to you what you prefer to use. However, Excel has something a lot more powerful with a lot more information in there, which actually can be a little daunting. But it's also very useful when you start to realize that linear regression doesn't need to simply be two coefficients. You can have multiple coefficients at a linear regression, especially as you're looking at multiple parameters in sequence, a summation of multiple steps. You can linearize across a wide range of independent values. So how do we do this? Well, before we can get into how we get to the regression tools, we have to first make sure that your Excel is properly set up. Now, I will state that unfortunately, I'm going to be giving this mainly for the Windows version of Excel and how to do this. You can get the regression tool in Macintosh, but it requires you to download a separate file from another website that's Excel that Microsoft uses. So I would encourage you just to go to Google and do a search for regression tool or analysis tool pack Excel for Mac, and it should come up. I think it's by a company called StatSoft, but I'll try to post links to that in a little bit. But anyways, how do you do it in Microsoft Windows version? So go to File, and in File you can go to your Options menu. And under Options, you'll get this little nice lovely thing pop up of, well, as you'd expect, options. And we can describe here some of these other options that we'll probably eventually play with. But what I really want you to go to is a section called Add-ons, and go all the way down to Manage Excel Add-ins, click Go. And this will pop up. And you want to make sure that your Analysis Tool Pack is selected, Analysis Tool Pack VBA, and your Solver add-in. Those are the ones that are most needed for this class. Solver add-in we'll deal with later in the semester, or in a couple weeks, or maybe next week even. But the Analysis Toolpack is what we're going to play with today. So just click OK. And if you have it, if you've done it correctly, you may need to restart. Depends on the version of Excel and how things are working. But if you go under Data, you'll see now Data Analysis and Solver as options under Analysis Options. So click Data Analysis, and you'll get this nice long list of a whole bunch of statistical analyses and things that are really beyond discussion in this class, except for, obviously, regression and the regression tool. So let's select that and click OK. Now here, I'm going to give as a rudimentary explanation of what all this is going to be output for you. There are key things I'm going to highlight that I think you should focus on. If you don't understand everything, that is fine. The most important thing is to understand how to get the coefficients out of this approach and how to understand or interpret what some of the data is and how to get the R-squared value. But with all that said, if you want to do regression, we'll do a regression on these raw data table like we did already. We can click Y input and select the Y input range. In this case, it's this. And I'm selecting, if you notice, Y as the label in that range. And then over here, I can select X and get that data label range as well. I include the data range label in there, so I have to tell that, yes, I have labels in the column selected. I can also specify whether or not we're going to go through the origin, that their constant in the system is 0. So if we go through the origin, force it through 0 or not. In this case, we won't force it through 0. And then finally, where do we want it to put the outputs from this result? I encourage you to always put a new worksheet. Why is that? You'll see as soon as you get the data, you don't want to have it buried on the same sheet, otherwise it gets really confusing. I think on a separate sheet is appropriate for most usages. And you can see it gives you a whole bunch of other stuff, things you may or may not care about. But let's just put residuals. You can, and residual plots. You can include other things if you want, but for the time being, I'll just leave those. Click OK, and here is the output. And the nice thing is, it's going to tell you a lot of things that you may or may not know of, and we won't go into too detail. The first thing is it gives a nice ANOVA, an analysis of variance on this on the approach. Again, if you're not familiar with what that means, it's kind of beyond the point of this class, so I won't go into that. But you'll see some things you recognize right away. R-squared value. Sure enough, you get the exact same R-squared value that you've seen before. Great. That's what you really care about in, here. It also gives you what they call an adjusted R-squared value. This adjusted R-squared value is used for when you have multiple X values, or it's another way of calculating it, and it accounts for the fact that as you add parameters, as you add conditions to model the data, just by the sheer fact that you have more variables to tune, your R-squared should go up. This adjusted R-squared value deals with that and gives you a more honest goodness of fit result of that. And then finally, looking over here, here's your coefficients table. And this is the most important thing, right? This is your coefficients. This is your intercept value, what you get, and this is your coefficient for the one parameter x. In other words, this is your slope value. And you'll notice it also gives you a standard error, which gives you the plus or minus around that coefficient. It gives you a sense of how reliable or how valuable that information is. And it also gives you a p-value. If you're familiar with statistics, p-value is a test against what they call a null hypothesis. In this case, the null hypothesis is this coefficient 0? Effectively, is there a coefficient or not? Does it exist or not? And the p-value of less than 0.05 is considered significant, that the value that's read here is not equal to 0. That's the meaning. And so yes, definitely it's not 0, so these values, these coefficients do exist. And then you have confidence intervals. We won't go into that. But this is really the most important part of this plot. But the nice thing also is you'll see residuals. It gives you a plot output that you can ask for that is the predicted y value for the model, what the model output is, and the residual, or in other words, the difference between this predicted value and the actual value for all the observations. And then you can plot that on a residual plot. And a good fit should hover around 0 and should have no trend to it. If you see a residual plot that looks like it's got a slope to it, or looks like the data isn't scattered randomly around this value, then you know that there is a trend that's built into your data that the model is just not accounting for. And so the residual plot can be useful in that regard, because it's just telling you that there's some systematic variation that you're not accounting for yet in your model, and you may want to change your model. So how do we get this information out of here then? The most important thing is you can just simply say copy, go back to your raw data, paste, and you have your intercept slope, and you can use this to recreate your data as you see fit. And that's it. That's all there really is to it. And if that's all there, but if that's all we could do, then the regression tool by itself isn't that interesting, nor is it that exciting. But we can do so much more. So let's do something else. And like I said, Regression Tool allows us to not just select a single x value of a single equation, like we're going to say y is equal to mx plus b as a simple linear equation. We could actually see any single set of parameters of x1, x2, x3, x4, any single value of parameters, a summation of independent parameters, get coefficients to y in a linear fashion, and sum those up and actually see how this models. What do I mean by that? Well, let's say, for example, I wanted to see how well or what kind of model we could set on this raw data, on this data here. What if we didn't want to use a linear expression to fit it, but let's say we said mx plus, and I'm going to start using ax plus, say, bx squared plus the c ln, or let's not, let's say c sine x. I'm just guessing on that one, and see if that and how that will fit the data. That's just, I'm kind of pulling that out of my head on this one. So we can say that, and let's go ahead and add new x parameters that each one fits here. So we have an x, we're going to want an x squared, and we're going to want a sine squared. So I'm going to create 2 more columns of independent values. And what I mean by independent values is that this expression x squared is an independent value. It's dependent upon x, but by itself we're just going to say it's its own its own column, it's its own behavior. So we can say x squared is equal to that squared, right? That's all that is. And down. And then, and I will capitalize that. And then we can say sine x. And I'll just say this is sine of this value. And copy and down. And so we have now sine x and x. And we can plot x squared versus y. We can plot sine x versus y. And now the question is, what coefficient can we place in front of x squared, sine x, and x to fit y the best? And we can use the linear regression tool to find that for us. So all we need to do is go back to data, go to data analysis, ask regression, and now this time for our y inputs we have here, our x input, we're going to say all of this. We have 3 columns, so it's going to treat each column of our x's as a new independent parameter in that linear regression, and everything else will keep the same. We'll have the labels there, and we get a whole new plot. And now you'll see we have an r² value that's present. The r² value, I believe, is slightly better than the one that we had before, because it probably fits a little bit better, but it's probably still not very good. And we have all new coefficients to use. So let's just see how this plots. So I'm going to copy this, go to our data, and I haven't run this before, so I have no clue what this is going to look like, but we'll see. And so we can create a y model. Okay, and for our y model, it's going to equal to this equation here, where our coefficients, this a, b, c, and the intercept d, which I did forget to give an intercept here, plus d. So just remember, that was the thing I forgot to do here, is a d-intercept. I had some intercept on here that I didn't add. But anyways, we can go down and look at the coefficients of each thing and see how this goes. So our first thing is our intercept gets no parameter, so we're going to have that, plus x squared. So that's going to be this coefficient times our x squared term, plus our sine x coefficient times sine x, plus our x coefficient times x. And we can copy and paste this down. And if we plot this, insert, let's see how this looks. Let's go with that. And I'm going to change this value to format data series. I'm going to change this into a line. So I'm going to have a solid line present. And then I'm also going to get rid of the data points. So you can go to markers and marker options, none. So we don't have data points now. We just have the fit. And you can see that's what the plot now looks like using the model ax plus bx squared plus c sine x. And you can definitely see you have the periodic motion of the sine function built in. You see the linear behavior that's present, as well as a very small exponential or a square term behavior as its data fits. So it fits the data slightly better, but it's really probably not significant. But it's just a nice way that you can have a now more complex equation that will allow us to fit a linear expression. When can't we use this? Well, for nonlinear expressions that can't be described in a linear term, like in the sense of where a parameter is going to be proportional to y. So in other words, I wouldn't be able to say or use the linear regression tool by looking at ax to the b power, a power law, for example. Because in this case here, ax to the b power, b is a coefficient that is a parameter that's going to model fit it, but it's not in a linear trend. It's not a proportionality to y. So as such, we can't use a linear regression tool to find this. Of course, we can, and this is described carefully in the PowerPoint slides, and I encourage you to look at this because this will be something that I can definitely, and I will definitely ask you on a quiz, for example, next Tuesday. Practice linearization. So for example, we could take this data, this equation here, this power law, and linearize it. What I mean by that is force it into a proportionality. Well, how can we linearize power models? Very simply by taking the log of both sides. If you remember taking the log of both sides, you can say that ln of y is going to equal to the ln of ax to the b. Well, what happens in that case then is we separate out that power. So I'm showing this through Excel, which is kind of weird, but that's fine. ln of a, we can separate the two terms, plus ln of x to the b. And if you remember, taking ln x to the b, this b term becomes a coefficient in front of the ln, so b. And in that case now, we have a linear expression of the ln of y versus the ln of a, where b is now the slope. And so we have a nice linear expression from this power law to this. So even if we have a nonlinear expression, oftentimes we can still use linear regression to find the parameters by linearizing expressions that we have. Now, we might not always be able to do this, and later in the semester, in a couple weeks, I'll show you how to do regression on functions that you can't do a linear regression on. You can do nonlinear regression, but for this time it's important to note that there are still a lot of ways you can plot data and get a linear response to. So I encourage you to study that and understand how to use that, because like I said, a linearization problem will be on a quiz on Thursday. So with all of that said, I hope that this section makes sense, and we will continue on to the next. Take care.